Welcome to this coding problem walkthrough. Today, we're tackling LeetCode problem number 2014, longest subsequence repeated k times. This problem challenges us to identify the longest subsequence of a string that repeats exactly k times. It's a fascinating question that tests your understanding of string manipulation and algorithm optimization. Let's dive right in. In this problem, you are given a string s of length n and an integer k. The goal is to find the lexicographically largest string t that can be repeated k times to form a subsequence of s. A subsequence is a string that can be derived from another string by deleting some or no characters while maintaining the order of the remaining characters. For example, if s is abc, both ab and ac are valid subsequences, but ba is not, because the order is changed. Additionally, for t to qualify, it must also be possible to repeat it k times and have the resulting string remain a valid subsequence of s. If no such string exists, the output must be an empty string. Let's explore some examples to clarify this further. In the first example, we are given s equals let's LeetCode and k equals 2. The output is let because let is a subsequence of s and can be repeated twice to form let, which is also a subsequence of s. There are no lexicographically larger strings that meet these requirements. In the second example, s equals bb and k equals 2. Here, the output is b, as the string b can be repeated twice to form bb, which is a valid subsequence of s. Since the input is very small, the solution is straightforward, and no longer or lexicographically larger string satisfies the conditions. In the third example, we have s equals abcd and k equals 2. The output is an empty string because there is no substring t that can be repeated twice and still form a valid subsequence of s. This showcases a scenario where the input constraints make it impossible to find a valid solution. As you can see, the problem requires careful consideration of how subsequences are formed and repeated. The key challenge lies in ensuring the string t satisfies both the subsequence condition and the repetition requirement while being as large as possible lexicographically. Now, let's discuss the constraints and some key edge cases. The length of s can go up to 7,000, and k can be as large as 2,000, which means the solution must be efficient to handle large inputs. One critical edge case is when k is too large relative to the occurrences of characters in s, making it impossible to construct a valid t. For example, with s equals abcd and k equals 2, no valid string t exists. Another key scenario involves small inputs, like s equals bb and k equals 2, where the solution should efficiently produce the correct result. For large inputs, the algorithm must efficiently navigate the constraints to avoid hitting time or memory limits. Finally, when multiple valid strings t are possible, the solution must always return the lexicographically largest one, ensuring correctness and consistency. To tackle the problem of finding the longest subsequence of a string s that can be repeated exactly k times, we considered several approaches. The first is the brute force approach, where we generate all possible subsequences of s and check how many times each one appears. The idea is to select the longest subsequence that appears at least k times. However, this method is computationally prohibitive because generating all subsequences is exponential, requiring (2 to the power of n) time, and verifying each one adds an additional (n) factor. With n going up to 7,000, this approach becomes infeasible. Therefore, we looked at optimized alternatives. One such method is backtracking, where we focus on candidates that are more likely to be valid solutions. By only considering characters that appear at least k times, we significantly reduce the search space. This refinement lays the groundwork for a more efficient solution. In the backtracking approach, we further optimize by exploring subsequences starting with the most frequent characters. Using a frequency map, we restrict our search to only those characters that appear at least k times, as others cannot contribute to a valid solution. For each candidate subsequence, we check if it appears k times in s using an efficient method, such as the two-pointer technique. This reduces the time spent on invalid candidates. Although faster than brute force, backtracking can still face challenges with large inputs. Another strategy we explored is breadth-first search, or BFS, where we systematically build longer subsequences from shorter ones. Starting with subsequences of length 1, we iteratively generate new candidates by appending valid characters. At each step, we verify if the candidate appears k times in S. This systematic exploration avoids redundant checks and benefits from pruning, though it may still involve overhead when n is large. The chosen strategy is optimized backtracking with pruning. The key observation driving this choice is that the solution must be a subsequence appearing at least k times in S. By focusing only on characters with a frequency of k or greater, we dramatically reduce the number of potential candidates. Backtracking allows us to systematically explore subsequences while pruning invalid branches early, avoiding the exponential blow-up seen in brute force. This approach is also well suited to the problem constraints, as checking if a subsequence appears k times can be done efficiently using 2 pointers. While BFS offers a systematic alternative, it may introduce unnecessary overhead compared to the more targeted nature of backtracking. The aha moment here is realizing that pruning based on character frequency simplifies the problem significantly, making the solution feasible even for larger inputs. Although the exact complexity depends on how effective the pruning is, this strategy is far more efficient than brute force and well suited to the given constraints. This problem challenges us to find the longest subsequence of a string S that can be repeated exactly k times. A subsequence is formed by deleting 0 or more characters from the string without altering the order of the remaining characters. However, the constraints make this problem particularly tricky. With the string length potentially reaching up to 7,000 characters and k values as high as 2,000, a brute force approach that generates all possible subsequences becomes computationally infeasible. This is because the total number of subsequences for a string of length n can grow exponentially, reaching up to 2 to the power of n. To solve this problem efficiently, we need a more optimized strategy. The solution involves pre-processing the string to reduce the search space, systematically generating candidate subsequences, and validating them while maintaining a balance between correctness and efficiency. Let's break it down step by step, starting with pre-processing and frequency analysis. First, we count the frequency of each character in the string using a hash map. Characters that occur fewer than k times can be eliminated immediately, as they cannot contribute to any valid subsequences. We then construct a filtered version of the string containing only these relevant characters. Next, we generate potential subsequences from this filtered string and validate them, ensuring that they can indeed be repeated k times in the original string. To efficiently generate and evaluate candidate subsequences, we use a breadth-first search, or BFS, approach. Starting with the shortest potential subsequences, those of length 1, we systematically explore longer subsequences. This method ensures that we find the longest valid subsequence without redundant computations or unnecessary exploration. For validation, we use a 2-pointer technique to check if a candidate subsequence can be repeated k times within the original string. One pointer iterates through the candidate subsequence, while the other scans the string S to determine whether the subsequence can be reconstructed the required number of times. To optimize further, we employ early pruning during the BFS traversal. If a candidate fails the validation check, it is immediately discarded, preventing unnecessary exploration of its longer extensions. Additionally, we keep track of the longest valid subsequence found so far. Once this maximum length is reached, we can stop exploring shorter candidates, saving computation time. Finally, the algorithm outputs the longest subsequence that meets the criteria of being repeated exactly k times. Key insights make this approach efficient and scalable to the constraints of the problem. First, frequency pruning allows us to discard irrelevant characters early, significantly reducing the search space. By focusing only on characters that appear at least k times, we minimize the computational overhead. Second, using BFS to explore subsequences in increasing order of length ensures that we find the longest valid subsequence efficiently, without needing to backtrack or recompute. Third, the 2-pointer technique for validating subsequences is highly efficient because it avoids explicitly reconstructing subsequences and instead directly checks their validity within the original string. The data structures used in this algorithm also play a critical role. We use a hash map to count character frequencies during the pre-processing step, a queue to manage BFS traversal, and a set to keep track of visited subsequences, ensuring that we don't reprocess the same candidate multiple times. The complexity of this approach depends on the number of candidate subsequences generated and the efficiency of the validation process. However, with careful pruning in BFS, the algorithm avoids the exponential growth of naive methods. For memory usage, the main factors are the storage of candidate subsequences and auxiliary structures like the queue and hash map. Lastly, it's important to handle edge cases, such as strings where all characters are unique or repeated characters lack sufficient frequency to meet the k requirement. Another edge case to consider is when the value of k is very large relative to the length of the string s. In such cases, it may become impossible to form any valid subsequence repeated k times, and the algorithm should handle this gracefully by returning an empty string if no valid subsequences are found. Now, turning to the pseudocode, the algorithm begins with frequency analysis using the counter class, which efficiently counts character occurrences. Characters that don't meet the frequency threshold are filtered out, leaving us with a reduced string of only relevant characters. A BFS approach is then implemented using a queue, where we initialize the queue with an empty string as the starting point. For each subsequence queued, we validate it using the is_valid function. If the candidate passes validation, we update the result and generate longer subsequences by appending each relevant character to the current candidate. This ensures that BFS explores all potential subsequences systematically, and validation is performed at every step to ensure correctness. Once the queue is emptied, the algorithm returns the longest valid subsequence found. The is_valid function plays a critical role in the validation step. It ensures that a given subsequence can be repeated exactly k times as a subsequence of the original string. The function uses a counter to track how many times the subsequence has been reconstructed so far and a pointer to iterate through the characters of the candidate subsequence. As the function iterates through the string s, it checks whether the current character matches the current position in the subsequence. If a match is found, the pointer moves forward, and when the end of the subsequence is reached, the count is increment. If the count reaches k, the function immediately returns true. Otherwise, the function continues scanning the string. If the string is exhausted before the subsequence is repeated k times, the function returns false. This efficient two-pointer approach ensures that we validate candidates without explicitly reconstructing them multiple times, making the algorithm both time-efficient and scalable for the given constraints. Here, we're implementing the solution to find the longest subsequence that is repeated k times within the string. First, we import the combinations function from the itertools module, which will help us generate all possible subsequences later. Next, we define the solution class and a helper method called is_subsequence. This method checks whether a given subsequence is a valid subsequence of the string s. It uses an iterator to ensure each character of the subsequence appears in order in the string. Then, we define the main method, longest subsequence repeated k, where we begin by counting the frequency of each character in the input string s. Using a dictionary, we increment the count for each character as we iterate through the string. Afterward, we filter out characters that occur fewer than k times, since they cannot possibly form a valid subsequence repeated k times. These filtered characters are stored in the candidates list, which we also sort lexicographically to ensure any resulting subsequence will be in the correct order. Next, we define a helper function called valid, which takes a candidate subsequence, repeats it k times, and checks if it forms a valid subsequence of the string using the is_subsequence method. This ensures that the candidate not only exists in the string but also meets the repetition criteria. Now, to find the longest subsequence, we generate all possible combinations of the candidate characters, starting with the longest possible subsequences. By iterating through lengths from n down to 1, where n is the number of candidates, we systematically explore all potential subsequences in decreasing order of length. For each combination, we check its validity using the valid function. As soon as we find a valid combination, we return it as the result by joining the characters into a string. If no valid subsequence is found after exploring all combinations, we return an empty string as the default case. This ensures the method always produces a result, either the desired subsequence or an empty string if no solution exists. With this approach, we efficiently narrow down the search space and ensure correctness by leveraging the helper functions and systematic generation of subsequences. Here, we start by importing the necessary libraries and defining our solution class. The first method, isSubsequence, is a helper function that checks if a string subsec is a subsequence of another string s. This is done using two pointers, one iterating over the main string s and another over the potential subsequence subsec. Whenever the characters match, the pointer for subsec moves forward, and the goal is to see if we can traverse the entire subsec within S. Next, we define our main method, longest subsequence repeated k, which takes two inputs, the string s and an integer k. We begin by constructing a frequency map to count how many times each character appears in the string. This allows us to filter out characters that occur fewer than k times, as they cannot possibly be part of a valid subsequence repeated k times. These filtered characters are stored in a list named candidates. Once we have the candidates, they are sorted lexicographically to ensure that any subsequences we generate will maintain the desired order for comparison. Next, we define another helper function, isValid, to check if a candidate subsequence, when repeated k times, is a valid subsequence of the original string s. This is done by repeating the subsequence k times and passing it to the isSubsequence method. After that, we move to the process of generating all possible subsequences. We start with the longest possible subsequences first, iterating from the length of the candidate list down to 1. For each length, we initialize a queue to manage our list of subsequences, starting with single characters from the candidates. As we iterate, we check if a subsequence is valid using the isValid function. If it is, we immediately return it as the result. If a subsequence is not valid, we proceed to generate longer subsequences by appending each candidate character to the current subsequence. This is done using a nested loop where each subsequence in the current queue is expanded by appending all possible candidates. These new subsequences are then added to the next queue for further processing. The process continues until the queue is empty, meaning all subsequences of the current length have been tested. If no valid subsequence is found after trying all lengths, we return an empty string as the result, indicating that there is no subsequence that meets the criteria of being repeated k times in the original string. This completes the implementation of the solution. To solve the problem, we start with the example where s equals ababab and k equals 2. The first step is to calculate the frequency of each character in the string. As we go through the string, we update the frequency dictionary. Initially, it's empty, but after processing each character, it gets updated, a 1 after the first a 1, b 1 after the first b, and so on. By the end, we find that both a and b appear 3 times, so the final frequency dictionary is a 3, b 3. Next, we filter these frequencies to identify candidates. These are the characters that appear at least k times. Since both a and b appear 3 times, which is greater than or equal to k equals 2, our candidates are a, b. Now, we move on to generating subsequences. Since we have two candidates, a and b, we try to construct subsequences of length 2. One possible combination is a, b, which forms the string ab. We then check if a repeated k equals 2 times, which is abab, is a subsequence of the original string s. Using the is_subsequence function, we verify this by matching each character in the repeated sequence abab with characters in s. We find matches for a, then b, then another a, and finally another b, confirming that abab is indeed a subsequence. Since this works, we return ab as the solution for this example. In the next example, we have s equals ab and k equals 3. The first step is to calculate the frequency of each character. Here, a appears 3 times, and b appears twice, leading to the frequency dictionary, a 3, b 2. After filtering for characters that appear at least k equals 3 times, we see that only a qualifies, so our candidates are a. Since there is only one candidate, we directly test it. The combination, a, repeated k equals 3 times forms the string AAA. Using the is_subsequence function, we check if AAA is a subsequence of s. By matching each a in AAA with the characters in s, we confirm that it is valid. Therefore, the solution for this example is a. Finally, consider the case where s equals abcd and k equals 2. First, we calculate the frequency of each character. Here, each character appears exactly once, resulting in the frequency dictionary of 1, b1, c1, d1. Since no character appears at least k equals 2 times, the candidate list remains empty. Without any candidates, it's impossible to generate a valid subsequence that meets the criteria. As a result, the solution for this example is an empty string. In this problem, the time complexity analysis begins with the frequency calculation. Here, we make a single pass through the string s to determine the frequency of each character, which takes n time, where n is the length of the string. Next, we filter out characters that occur fewer than k times. Since the frequency dictionary contains at most 26 entries, corresponding to the lowercase English letters, this step is performed in 1 time. After filtering, the algorithm generates all possible combinations of the remaining candidates. Let m represent the number of valid candidates after filtering. The combinations are generated for lengths ranging from m down to 1, resulting in a total of 2 to the power of m1 combinations. This operation takes 2 to the power of m time, where the exponential growth of combinations quickly becomes the dominant factor as m increases. Now, each of these generated combinations must be checked for validity. For a given combination, the algorithm constructs the repeated subsequence, which involves concatenating the combination k times. This takes k asterisk length underscore of underscore combination time. Then, the is_subsequence function is used to verify if this repeated sequence is a valid subsequence of the string s. This check iterates through s and, in the worst case, takes n time. Let the length of the combination be L. The total cost for a single validity check is therefore k asterisk L plus n. Since there are 2 to the power of m combinations to check, the total cost for this step becomes 2 to the power of m asterisk k asterisk m plus n. Combining all the steps, the overall time complexity of the algorithm is dominated by this term, 2 to the power of m asterisk k asterisk m plus n. It is important to note that m is always less than or equal to 26, as it is limited by the alphabet size, making the exponential factor 2 to the power of m the primary driver of the complexity. Turning to space complexity, the algorithm first uses a frequency dictionary to store counts for at most 26 characters, which requires 1 space. After filtering, the list of valid candidates also contains at most 26 characters, so this step also uses 1 space. When generating combinations, the algorithm does not store all combinations in memory simultaneously, instead, it processes them one at a time. This means the space required for combinations is bounded by the size of the largest combination, which is m. For subsequence construction during validity checking, the space required is k asterisk m, as the repeated subsequence includes k copies of the combination. Lastly, the is_subsequence function uses an iterator that is memory efficient, so it does not require additional storage proportional to the length of s. These factors combine to give an overall space complexity dominated by k asterisk m. The final space complexity remains k asterisk m, as this is the largest contribution from subsequence construction. Analyzing best, average, and worst-case scenarios helps us understand the algorithm's behavior further. In the best case, the algorithm finds a valid subsequence early in the process, which reduces the number of combinations it needs to check. Here, the time complexity approaches 2 to the power of m, as fewer validity checks are required. In the average case, a significant portion of the combinations is explored before finding a valid subsequence, leading to the full complexity of 2 to the power of m asterisk k asterisk m plus n. In the worst case, every combination is checked, and each validity check involves processing the entire string s. This results in the same overall complexity, with the exponential term dominating due to the growth of 2 to the power of m. Comparing this approach to a brute force solution highlights the optimization gains. A naive approach would generate all possible subsequences of the string s, resulting in 2 to the power of n total subsequences. This is computationally infeasible for large n. The given solution, on the other hand, significantly reduces the search space by focusing on subsequences of frequent characters. Since m is limited to 26, the search space is reduced to 2 to the power of m combinations, which is a dramatic improvement. Additionally, the algorithm leverages character frequency and lexicographical ordering to prune unnecessary computations. However, the exponential dependency on m, specifically 2 to the power of m, remains a bottleneck. In terms of mathematical proof, the time complexity stems from generating and validating combinations. With at most 2 to the power of m combinations in each validity check taking k asterisk m plus n, the total complexity is 2 to the power of m asterisk k*m plus n. Space complexity, primarily driven by the subsequence construction, is O, k*m, as discussed earlier. When solving this problem, there are a few common mistakes to watch out for. First, developers sometimes forget to consider the exact constraint on k, which means they might generate subsequences without ensuring that they repeat exactly k times in the original string. This can lead to either incorrect results or wasting time on unnecessary computations. To address this, always verify that a candidate subsequence can indeed repeat k times by simulating its repetition and checking its presence. Another frequent issue is relying on a brute force approach for large inputs. For example, generating all possible subsequences of a string has an exponential time complexity and becomes impractical for strings with a length of 7,000 or more. Instead, focus on leveraging properties of the problem, such as subsequence pruning and frequency constraints, to narrow down the search space. Lastly, some solutions overlook the importance of character frequencies. If a character doesn't appear at least k times in the original string, it can never form part of a valid subsequence. By filtering out such characters early, you can save significant computation time and avoid invalid candidates. Another significant challenge involves inefficient string matching techniques. For instance, naively checking whether a candidate subsequence exists in the original string by scanning it repeatedly can result in excessive runtime, especially for longer strings. A more efficient approach is to use a two-pointer method or index-based traversal to verify subsequences. Additionally, when multiple valid subsequences of the same length are possible, it's easy to overlook the requirement to return the lexicographically smallest one. This is a common oversight that can lead to incorrect answers. To avoid this, ensure the subsequences are either generated in lexicographical order or sorted appropriately before returning the result. Incorporating these optimizations will make your solution both efficient and correct. This problem is a great opportunity to demonstrate key skills during an interview. It tests your ability to balance correctness and efficiency when working with subsequences. Recognizing that character frequencies can help prune invalid candidates is a critical insight interviewers look for. They may also evaluate your ability to optimize brute force approaches, so be ready to explain how you reduce unnecessary computations. It's also important to prepare for follow-up questions. For example, you might be asked how your solution handles edge cases, like when k equals 1, strings with all identical characters, or highly unbalanced frequency distributions. Additionally, interviewers may extend the problem by increasing constraints or asking you to discuss variations. Finally, emphasize the importance of thoughtful test case design. Use examples like empty strings, strings where every character is unique, or strings with uneven frequency distributions to showcase the robustness of your solution. There are several related problems that can help you build the skills needed to solve this challenge. For example, LeetCode 392 is Subsequence, focuses on efficiently verifying whether one string is a subsequence of another, which is a key part of this problem. LeetCode 791, Custom Sort String, involves sorting characters based on a given order, which can be useful when handling lexicographical constraints. Another relevant problem is LeetCode 524, Longest Word in Dictionary through Deleting, which also involves verifying subsequences but with a focus on dictionary words. Finally, LeetCode 139, Word Break, shares principles of dynamic programming for segmenting and validating strings, which can inspire alternative approaches to this problem. Exploring these problems will deepen your understanding and enhance your problem-solving toolkit. There are also alternative approaches to solving this problem, each with its own trade-offs. One option is backtracking with pruning, where you generate subsequences recursively but eliminate branches early if the character frequencies are insufficient or the current subsequence exceeds the maximum length. While this method is intuitive, it can still be slow for very large inputs. Another approach is breadth-first search, or BFS, where you explore subsequences level by level to ensure you find the longest valid subsequence. This method is efficient for shorter strings but can become memory-intensive as input size grows. Finally, dynamic programming provides another powerful strategy. By tracking valid subsequences and their lengths, you can reduce redundant checks. However, implementing DP to handle lexicographical constraints can be complex. Each of these methods offers valuable insights and can be chosen based on the specific requirements or constraints of the problem. Great work! In this walkthrough, we explored how to find the longest subsequence repeated k times. We discussed strategies for optimizing the solution and drew out key takeaways for similar problems. Thanks for watching. Don't forget to like, subscribe, and share for more coding solutions and insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!